Hari Om. Hello everyone, I am Shrees. Welcome back to my channel. Today we are going to study class 12 mathematics chapter 1 relations and functions. In class 11 we have already learnt about relations and functions, their domain, codomain and range. Usually the relation is used in connection between two objects or quantities of each other, right? But in mathematically, a relation are from a set A to a set B is the subset of Cartesian product A cross B obtained by describing the relationship between first element X and the second element Y of ordered pairs in A cross B. That means all the elements belongs to A cross B. That means relation is the subset of Cartesian product A cross B. We have already learned what is the Cartesian product in sets in class 11th, right? Okay. So here, for example, that means all the elements of relation is in the form of ordered pair xy. X is the first element, y is the second element. So here, for example, x to x. See here, second element is the twice of first element. 416. Here, second element is the square of first element. Okay, so these all things we have already learnt in 11th standard. So here in this chapter we will study types of relations. Types of relations. So for that, okay, see here, first of all let us take a set, non-empty set A, and we know that a relation R is the subset of, R is a subset of A cross A. Okay, a relation R is a subset of A cross A. That is, all the subsets of A cross A is a relation in A. Okay, and here we know that phi, that is an empty set, and A cross A are the subset of A cross A, isn't it? In sets we have already learned phi is the subset of all sets, right? And see, suppose here A is a set. A is subset of A itself, right? So therefore, here also we can say phi and phi means null set, empty set and A cross A are the subsets of A cross A, right? Therefore, here phi is a relation in A and A cross A is a relation in A. Okay, so phi is a relation in A. Phi is a relation in A, and also A cross A is a relation in A. So this relation, okay, phi is a relation, therefore this relation is called an empty relation, and this relation is called a universal relation, okay. Phi is called an empty relation and A cross A, it is called a universal relation. See here, there is no element in this relation, okay, that is empty, okay, empty relation. So it is called empty relation. So A cross A, this relation has all the elements of A cross A, right? So this relation is called universal relation. For example, let us take an example for empty relation and universal relation. So let us take a set, let A is equal to 1, 2, 3, 4. Okay. And define two relations, R1, define R1 and R1B, set of AB such that A plus B is equal to 10. Okay. We defined a relation R1 such that AB, because here all the elements of relation in the form AB, ordered pair AB. AB such that A plus B is equal to 10. It is the condition. Okay. So here let us define another relation R2 such that AB, ordered pair AB, A plus B less than 10. Okay. So we have defined two relations R1 and R2. Okay, now let us see what about R1. See what are the elements of R1. Here R1 is nothing but AB such that A plus B is equal to 10. Okay, so here AB are these elements. Okay. So here, what are the elements of R1? Here we observe that for any two elements in this set, for any two elements, A plus B not equal to 10. Right? Why? Because see, take 1 plus 2 is a 3, 2 plus 4 is a 6, 3 plus 4 is a 7. Okay. So here we observe that for any two elements, A plus B not equal to 10. Okay. Therefore, there is no element in R1. So we say that this R1 is an empty set and this relation R1 is called an empty relation. Okay. So this R1 is an empty relation. And what about R2? See, R2 here for any two elements, see, 1 plus 2 is 3, that is less than 10. 1 plus 3 is 4, that is less than 10. 2 plus 4 is 6, that is less than 10. So here for any two elements in A, we observe that A plus B less than 10. Okay, for all the elements. Okay, here if you take any two elements in A, then their sum is less than 10. Okay, therefore here R2 containing all the elements of A cross A. Okay, see, if you find A cross A, what is A cross A? See, A cross A will be 1 1, 1 2, 1 3, 1 4, right? 1 5, 1 6, sorry, 2 1, 2 1, 2 2, 2 3, 2 4, etc. Okay. So here you know already how to write A cross A. So here we will get R2 containing all the elements of A cross A, because if we take for any two elements of in A plus B less than 10. Okay. Therefore R2 containing all the elements of A cross A. Okay. That means here R2 is a universal relation, because R2 containing all the elements of A cross A, therefore R2 is a universal relation. Okay. So R2 is a universal relation. Now let us go through an example. Let R be the relation on the set n of natural numbers given by R is equal to set of ordered pair AB such that A minus B greater than 2, B greater than 3. Choose the correct answer. See here, B, it is given that these are the conditions: A minus B greater than 2, B greater than 3. See, it is given B greater than 3, therefore this first one is not possible, right? Because here B value is 1, it is given that B greater than 3. Okay, so it is not possible. Now let us check one by one among these three. Okay, so here 8 7. A minus B greater than 2. See here it is okay, right? B is greater than 3 and A minus B greater than 2. Here 8 minus 7, that is 1. So 1 is not greater than 2. So it is not a correct answer. Okay. So now let us go to this one. Here 5 minus 8 is minus 3. Okay. So here minus 3 is not greater than 2. Minus 3 is less than 2. Therefore it is not a correct answer. So now let us come to here. 10 minus 6 is 4. 4 is greater than 2. And B, that is 6. 6 is greater than 3. Therefore it is a correct answer. That is D. 10 6 belongs to R. Look at the second example. On the set R of real numbers, S is a relation defined by S is equal to set XY, ordered pair XY such that X belongs to R, Y belongs to R, X plus Y is equal to XY. Find A belongs to R such that A is never the first element of an ordered pair in S. Also find B belongs to R such that B is never the second element of an ordered pair in S. So here it is the condition X plus Y is equal to XY, given relation defined by XY such that X belongs to R, Y belongs to R, X plus Y is equal to XY. So here we have to find the value of A. A means the first element of an ordered pair. Okay, B is first element, second element of an ordered pair. Okay, so here we have to find the value of A, which is never the first element in ordered pair in S. Okay, and B, which is never the second element of ordered pair in S. Okay, so for that, let us take an element from S. Okay, that means, see, let ordered pair AB belongs to S. We have taken an element from S. Okay, so since AB belongs to S, A plus B is equal to AB according to the condition, right? A plus B, this implies A plus B is equal to AB because this AB belongs to S. And here, now let us simplify this one. Here, take A right side. So, B is equal to AB minus A, that implies A into B minus 1. Okay, that implies B is equal to B is equal to A into B minus 1. So here B by B minus 1 is equal to A. Okay, take B minus 1 left side. So here we have got A is equal to B by B minus 1. See, when B is equal to 1, this will not be defined, right? When denominator is 0, it will not be defined, right? Therefore, B should not be 1. Okay, because if B is equal to 1, denominator will be 0, right? B is equal to 1 minus 1, it will be 0, so it will not be defined. Therefore, here B should not be 1. Okay, B value should not be 1. And another, see, another simplification. Here we can take same equation from the equation A plus B is equal to AB. A plus B is equal to AB implies, take B right side. Okay, so A is equal to AB minus B. So A is equal to B into A minus 1. So A divided by A minus 1 is equal to B. See, here also we have got in denominator A minus 1. So here also A should not be 1, because if A is equal to 1, it will not be defined, right? So 1 minus, because A minus 1, 1 minus 1, it will be 0. Therefore, if A is equal to 1, it will not be defined. Therefore, here also A should not be 1. A not equal to 1. Okay. So, if an element from S, okay, if it is an element from S, A should not be 1 and B should not be 1. Okay. So, here itself we can say when A is equal to 1, see, A is equal to 1 is the value which is never the first element of an ordered pair in S. Okay. And B is also, B is equal to 1 which is never the second element of an ordered pair in S. Okay. Why? Because see, according to our condition, here A should not be 1 and B should not be 1. Therefore, here we have to find the value of first element and second element which is never the first and second element of ordered pair in S. Okay. If an element in S, see, it should not be 1. A should not be 1, B should not be 1. Right? Therefore, our answer is A is equal to 1 and B is equal to 1. Okay, which are never the first element and the second element of the ordered pairs in S respectively. Okay, therefore A is equal to 1 which is never the first element of ordered pair in S, and B is equal to 1 which is never the second element of an ordered pair in S. Next type of relation is equivalence relation. Equivalence relation. Okay. So let R be a relation. R be a relation on a set A. Set A. Okay. And here let us take an element. If A ordered pair A belongs to R, for every A belongs to A. For every A belongs to A. Okay. If ordered pair A belongs to R, for every A belongs to A. Okay. So this relation is called reflexive. This relation is called, here R is called reflexive. Reflexive relation. And next, if AB belongs to R, then BA, ordered pair BA belongs to R. Okay. So this relation is called symmetric relation. Okay. R is called symmetric relation. Okay. And third one, if AB belongs to R and BC belongs to R, then AC belongs to R. Okay. AB belongs to R, BC belongs to R, then AC belongs to R. Okay. This relation is called transitive relation. Here R is called transitive relation. Transitive relation. So if the relation R in a set A is said to be an equivalence relation if the relation is reflexive, symmetric and transitive. Okay. If a relation R is reflexive, symmetric and transitive relation, then we say that that relation is an equivalence relation. Okay. If a relation is reflexive, symmetric and transitive, then this relation is called equivalence relation. Next example, show that the relation R in the set 1, 2, 3 given by R is equal to, it is the given relation, okay. These are the elements of this relation. Ordered pair 1, 2, 2, 1 is symmetric but neither reflexive nor transitive. See, according to definition, what is symmetric? Symmetric is nothing but a relation R is in the set A, okay. Then AA, ordered pair AA belongs to R for every A belongs to A. Okay. Here, see, here the set A is nothing but set 1, 2, 3 and the relation is 1, 2, 2, 1. Okay. And here, see, if we say reflexive means 1, 1, 2, 2, these are the elements of A, 2, 2, 3, 3 should be belongs to R. Okay, should be elements of R. But here, no 1, 1 belongs to R, no 2, 2, no 3, 3. Right? Therefore, we can say here this relation is not a reflexive relation. Okay, because our set is 1, 2, 3. So to set it is a reflexive relation. There 1, 1, 2, 2 and 3, 3 should be in the set R. Okay, but here there is no 1, 1 and 2, 2, 3, 3. Therefore, here we can say since 1, 1 not belongs to R, so this R is not reflexive relation. Okay, since 1, 1 does not belongs to R, therefore R is not reflexive. Okay, and next is symmetric. See, here we know that what is a symmetric according to definition. If AB belongs to R, then BA belongs to R. Okay, if AB belongs to R, then BA should be in R. Take one element, 1, 2. 1, 2 is belongs to R. 2, 1 is also belongs to R. Okay, or take 2, 1. 2, 1 belongs to R, then 1, 2 belongs to R. Therefore, this R is symmetric. Okay, R is symmetric relation. But here next third one. So here you can write 1, 2 belongs to R and 2, 1 belongs to R. Therefore, R is symmetric. What about the transitive? See, what is the transitive definition? If AB belongs to R and BC belongs to R, then AC belongs to R. Okay. So here let us take, see, 1, 2 belongs to R and 2, 1 belongs to R. Okay, 1, 2, 2, 1. Okay, AB, BC. But 1, 1 does not belongs to R. Okay, 1, 1 does not belong to R. Therefore, R is not a transitive. Okay, here we can write 1, 2 belongs to R and 2, 1 belongs to R, but 1, 1 does not belong to R. But 1, 1 does not belongs to R. Therefore, R is not transitive. Okay. Next example. Let A be the set of all human beings in a town at a particular time. Determine whether of the following relation is reflexive, symmetric and transitive. So first one given relation is R is equal to ordered pair xy such that x and y work at the same place. So here now let us check first one. See, given relation is ordered pair xy such that x and y work at the same place. See, first of all let us check whether this relation is reflexive or not. See here, x and y work at the same place, then xy belongs to R, right? So we have to prove according to the definition, reflexive is x should be belongs to R, right? Now let us check. See, x and y work at the same place. So we can say x and x work at the same place, right? X and x work at the same place. Okay. So here x belongs to R, right? Because we can say x and x work at the same place. Okay. If x is working at the same place, x and x work at the same place. So here x belongs to R. Okay. Therefore, this relation is reflexive. Okay, we say this relation is reflexive. Then what about symmetric? See, x and y work at the same place. We can say y and x work at the same place, right? X and y work at the same place means y and x work at the same place also, right? So therefore, if xy belongs to R, here xy belongs to R, xy belongs to R and yx is also belongs to R, right? xy work at the same place, then yx is also y and x work at the same place. Therefore, yx belongs to also x, right? So here xy belongs to R, then yx belongs to R. According to definition, it is this relation is symmetric. Okay. Now let us take another element. Okay, xy belongs to R. Xy belongs to R. For transitive, we have to take another element. Okay, now let us take yz belongs to R. Okay, xy belongs to R and yz belongs to R. We have taken an element from R, that is yz belongs to R. Okay, that means according to the relation definition, yz belongs to R means y and z work at the same place. Okay, y and z work at the same place. See, x and y work at the same place, okay, and y and z work at the same place. That means x and z work at the same place, isn't it? See, just imagine x and y work at the same place, okay. So y and z work at the same place, okay. So y and z work at the same place, x and y work at the same place. Okay, so in both the sentence y is there, right? So they four means 3 x, y and z work at the same place, right? Therefore we say x and z work at the same place. That means xz belongs to R. Xz belongs to R. Okay, if xy belongs to R and yz belongs to R, then xz belongs to R. So according to definition, here R is transitive also. Okay. So in first relation R is reflexive, symmetric and transitive. Therefore, this relation is an equivalence relation. This one no need, because here we have to only check whether this relation reflexive, symmetric and transitive. Okay. So first relation is reflexive, symmetric and transitive. Now what about second relation? See, second one, xy such that x and y in the same locality. Okay, see, it is similar to first one, right? So x and y in the same locality. So here also we can say x and x live in the same locality, right? So here we say x belongs to R. Therefore this relation is reflexive. Okay, according to the definition, this relation is reflexive. Okay, x belongs to R. And what about symmetric? xy belongs to R, right? See, here we can say xy belongs to R means x and y live in the same locality. Now we can say y and x live in the same locality. Okay, conversely we can say y and x live in the same locality, right? That means yx belongs to R. Okay, x and y live in the same locality means xy belongs to R, right? So y and x live in the same locality means yx belongs to R. Okay, so yx belongs to R. So xy, if xy belongs to R, then yx belongs to R. Therefore this relation is symmetric. Okay, now what about transitive? See, transitive also. Here xy belongs to R. Okay, xy belongs to R. And let us take another element from R, that is yz belongs to R. Okay, since these are the elements of R, x and y live in the same locality, y and z live in the same locality. Okay, x and y live in the same locality, y and z live in the same locality. That means these three, x, y, z, are live in the same locality. That means we can say x and z live in the same locality. Okay, x and z live in the same locality means xz belongs to R. Okay, x and z live in the same locality means xz belongs to R. So here also we have got, if xy belongs to R and yz belongs to R, then xz belongs to R. Therefore this relation is transitive. Okay, therefore this relation is reflexive, symmetric and transitive. Now what about third one? Third one, see here, the sentence, the relation is ordered by xy such that x is wife of y. X is wife of y. So here for reflexive, according to the definition, can we say x is wife of x? X is wife of x. It is not possible, right? X is wife of only y. Okay, therefore x is wife of x is not possible. Okay, therefore here x does not belongs to R. Does not belongs to R. Okay, here x does not belong to R. Why? Because it is not possible. X is wife of x. X is wife of only y, right? So x is wife of x is not possible. Therefore this element, that is x order pair x does not belong to R. Therefore this relation is not reflexive. Okay, not reflexive. Next, what about symmetric? Let us see. X is wife of y. Can we say y is wife of x? Not possible, right? Y is husband of x, right? So if x is a wife of y is husband of x. So not y is wife of x, right? So here also yx does not belongs to R. Okay? Why? Because if x is wife of y is not wife of x. Y is husband of x, right? Therefore, it is also not possible. This sentence, y is wife of x, is not possible. Right? Therefore, this element, that is yx, does not belong to R. So, this relation is not symmetric too. Okay? Next, transitive. Okay, x is wife of y. That is, okay, here for transitive, let us take two elements from R. That is, xy belongs to R and yz belongs to R. Okay, xy belongs to R means x is wife of y. Okay, x is X is wife of Y, right? And YZ belongs to R means Y is wife of Z. Okay. So here see, X is wife of Y, Y is wife of Z. See, it is not possible X is wife of Z. See, it is also not possible. See, X is a wife of Y and Y is a wife of Z. So, there will not be the ordered pairs in the form of XY and YZ. Okay. So, here in this set in R, there will not be the ordered pairs in the form of XY belongs to R and YZ. XY and YZ. Because this sentence is X is the wife of Y and we cannot say Y is the wife of Z. Okay, X is the wife of Y means Y is the husband, right? Husband of X. So it is not possible. Therefore, here we can say R is transitive because there is no element, that is no ordered pair in the form of XY and YZ. XY and YZ. Okay. Therefore, this relation is transitive. Okay. And next, fourth one. Set XY such that X is the father of Y. X is father of Y. It is also similar to third one, right? So, X is father of Y. See, reflexive. X is the father of X. Not possible, right? Therefore, XX does not belong to R. So, this relation is not reflexive. Symmetric. See, X is father of Y. Y is the father of X. Not possible, right? So, Y is son of X or daughter of X, right? So, therefore, X is the father of Y. It does not imply Y is father of X. Therefore, here Yx does not belongs to R. Therefore, this R is not symmetric. And what about the transitive? See, X is the father of Y. Okay. So, here also we will take two elements from R. XY belongs to R and YZ belongs to R. So, XY belongs to R means X is father of Y. X is father of Y. Okay. And YZ belongs to R means Y is father of Z. Okay. X is father of Y and Y is father of Z. Okay. So here can we say X is father of Z? No, right? Because if X is the father of Y, Y is father of Z, that means, see, X is father of Y, okay, and Y is father of Z, that means X is grandfather of Z, right? So, we cannot say X is father of Z, okay. These elements belongs to R. It can be belongs to R, okay. XY belongs to R and YZ belongs to R. XY belongs to R means X is father of Y, okay. And YZ belongs to R means Y is the father of Z. But X is not father of Z, okay. It is not possible. X is father of Z. It is not possible. Therefore, here XZ does not belong to R. Okay, XZ does not belong to R because X is father of Z is not possible. Because here X is father of Y and Y is father of Z. Therefore, here X is father of Z is not possible. That means XZ does not belong to R. So, if XY belongs to R and YZ belongs to R, then XZ does not belong to R. Therefore, this relation is not transitive. Okay, not transitive. So, last relation is not reflexive, not symmetric and not transitive. Let us go through next question. Show that the relation R on the set Z of integers given by R is equal to set ordered pair AB such that 2 divides A minus B is an equivalence relation. Given condition is 2 divides A minus B. It is the defined relation. So here we have to check whether this relation is an equivalence relation or not. So for that we have to check reflexive, symmetric and transitive. Okay, so given relation is R is equal to ordered pair AB such that 2 divides A minus B. Okay, so here we can say 2 divides A minus A, right? Because 2 divides A minus A. 2 divides A minus A means 2 divides A minus A. That is 2 divides 0, right? 2 divides 0 means 0 divided by 2, that is nothing but 0. So it is also possible 2 divides 0. Okay, therefore 2 divides 0 is correct. Therefore we can say 2 divides A minus A. So 2 divides, if 2 divides A minus A belongs to R, right? So here we can say 2 divides A minus A because we know that 2 divides 0. Okay, so here we can say 2 divides A minus A. That means AA, ordered pair AA belongs to R. So since AA belongs to R, this R is reflexive. This R is reflexive. Okay, next, because AA belongs to R. Okay, since 2 divides A minus A, if 2 divides A minus A, AA belongs to R. Since AA belongs to R, R is reflexive. Next, see, we can say 2 divides C, if 2 divides A minus B, okay, if 2 divides A minus B, then 2 divides B minus A also, right? See, 2 divides A minus B means, suppose A minus B is 5. Okay, 6, okay, 2 divides 6, okay. 2 divides A minus, suppose A minus B is equal to 6. Then what will be B minus A? That is nothing but minus 6, right? B minus A is minus 6. So here, if 2 divides A minus B, if 2 divides 6, then 2 divides minus 6 also, right? Because minus 6 by 2 is minus 3, okay? 6 by 2 is 3. So if 2 divides A minus B, then 2 divides B minus A too. Okay, so 2 divides B minus A. If 2 divides A minus B, then 2 divides B minus A. Therefore, here BA belongs to R. Okay, if AB belongs to R, then we can write, if AB belongs to R, then BA belongs to R. Why? If 2 divides A minus B, then 2 divides B minus A. So here we can write, see, I will write the steps. AB belongs to R, that implies 2 divides A minus B, right? According to the definition, relation definition. Then that implies 2 divides B minus A. Okay, that implies, if 2 divides B minus A, that implies BA belongs to R. Okay, according to the relation. Okay, BA belongs to R. If 2 divides B minus A, then BA belongs to R. So we have got, if AB belongs to R, then BA belongs to R. Therefore, this R is symmetric. Okay, R is symmetric. Next, we have to prove it is transitive. Okay, so for transitive, let us take two elements from R. Okay, let AB belongs to R and BC belongs to R. Okay, since AB belongs to R, 2 divides A minus B, right? According to the definition of relation. 2 divides A minus B, and here BC, since BC belongs to R, 2 divides B minus C. Okay, since BC belongs to R, 2 divides B minus C. 2 divides B minus C. That implies, see here, 2 divides A minus B and 2 divides B minus C. See here, if 2 divides 6, okay, and 2 divides 4, then we can say 2 divides 6 plus 4. Okay, that is 10. 10 is also 2 divides 10 also. Okay, so here also we can say if 2 divides A minus B and 2 divides B minus C, then 2 divides their sum. That is A minus B plus B minus C. That implies 2 divides, here minus B plus B cancelled, A minus C. So 2 divides A minus C. So 2 divides A minus C implies AB belongs to R. Okay, 2 divides A minus C implies ordered pair AC belongs to R. So this implies ordered pair AC belongs to R. So we have got ordered pair AB belongs to R and BC belongs to R, then AC belongs to R. Therefore, this relation is transitive. R is transitive. Therefore, R is reflexive, symmetric and transitive. Therefore, this relation is an equivalence relation. Okay. Therefore, given relation is an equivalence relation. Look at the next question. Let L be the set of all lines in a plane and R be the relation in L defined as R is equal to set ordered pair L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. So here L is the set, okay, set of all lines in a plane, okay, and R is the relation in L and it is defined as ordered pair L1, L2 such that L1 is perpendicular to L2, okay. So here now for that, here we have to check whether it is reflexive. Okay, we have to prove R is symmetric but neither reflexive nor transitive. Oh, okay, now let us go through reflexive first one. So according to definition, reflexive definition, see L1 should be in R, right? But here, see, our condition is relation definition is L1 is perpendicular to L2. Okay, L1 is perpendicular to L2, then L2 belongs to R. Okay, so here can we say L1 perpendicular to L1? Not possible, right? So we cannot say L1 perpendicular to L1, right? L1 perpendicular to L1 perpendicular to L2, but L1 is not perpendicular to L1. Okay, therefore here we cannot, here L1 is not perpendicular to L1, therefore L1 does not belong to R. Okay, so L1 is not perpendicular to L1. Okay, since L1 is not perpendicular to L1, okay, so L1 does not belong to R. Okay, therefore this relation is not reflexive. Okay, therefore R is not reflexive. Okay, next is symmetric. See, L1 is perpendicular to L2. Now we can say L2 is perpendicular to L1. L2 is perpendicular to L1. L1 is perpendicular to L2. L2 is also perpendicular to L1. Okay. So here we can say L2 is perpendicular to L1. Therefore L2, L1 belongs to R. Okay. According to the definition of relation. See, L1 perpendicular to L2. L2 perpendicular to L1. Therefore L2, L1 belongs to R. That is L1, L2 belongs to R implies L1 is perpendicular to L2. Okay, that implies L2 is perpendicular to L1. That implies L2, L1 belongs to R. That is, we have got if L1, L2 belongs to R, then L2, L1 belongs to R. Therefore, this relation is symmetric. Okay. Therefore, this relation R is symmetric. Now what about the transitive? Now let us see. Let us take one more element. See, L1, L2 belongs to R. Okay, L1, L2 belongs to R and L2, L3 belongs to R. Okay, L1, L2 belongs to R means L1 is perpendicular to L1, L2, L2, okay, and L2 is perpendicular to L3, okay, L2 is perpendicular to L3, okay, L2 is perpendicular to L3, okay, L1 is perpendicular to L2, okay, and L2 is perpendicular to L3. Now can we say L1 is perpendicular to L3? L1 is perpendicular to L3. Is L1 perpendicular to L3? Is L1 perpendicular to L3? No, right? L1 is not perpendicular to L3. L1 and L3 are parallel, right? So L1 is not perpendicular to L3. So we cannot say here L1 is perpendicular to L3. Therefore, L1, L3, this implies L1 is not perpendicular to L3. This implies L1, L3 does not belong to R. Okay. So here we have got L1, L2 belongs to R, L2, L3 belongs to R. Then and L1, L3 does not belong to R. Therefore, this relation is not transitive. Okay. Therefore, hence this relation is this relation is symmetric but neither reflexive nor transitive. Look at next question. Give an example of a relation on a set A is equal to set 1, 2, 3, 4 which is reflexive and symmetric but not a transitive. So here we have to write the relation. Okay, example for relation which is reflexive and symmetric but not a transitive in the set A. Okay, so here it is reflexive, right? So therefore let us write all the elements, that is 1, 1, 2, 2, 3, 3. For reflexive, these elements should be in R, right? 4, 4. And it is symmetric also. Now let us write 4, 2, 2, 4. Okay. And next I will write 4, 2, 4 is here. For not transitive, 2, 4 and 4, 3. Okay. 4, 3. So here I wrote 4, 3, therefore I should write 3, 4 also because it should be symmetric, right? So 4, 3, for this 4 symmetric I should write 3, 4. Okay, now let us take for reflexive it is okay. Then 4, 2 is there, 2, 4 is here, right? And 4, 3, 3, 4 is here. Okay, then after that, see here, for not transitive, 2, 4 belongs to R, 4, 3 belongs to R, but 2, 3 does not belong to R, right? 2, 3 is not in this set, right? Therefore, we can say it is an example for relation which is reflexive, symmetric but not transitive in A, okay? Because see, for reflexive, 1, 1, 2, 2, 3, 3, 4, 4 belongs to R. And for symmetric, 4, 2 belongs to R, 2, 4 belongs to R. And for not transitive, we should write 2, 4 belongs to R, right? So next, starting from 4, 4, 3 belongs to R. See, for symmetric, we should be careful here. For symmetric, see, if we write 4, 3, so we should write 3, 4 also because it should be symmetric, okay? And for not transitive, see, take these two elements, 2, 4 and 4, 3, but 2, 3 is not in this set. So if you write 2, 3, just cancel it. 2, 3 should not be in this set because 2, 4, 4, 3 for not transitive, write 2, 4, 4, 3 but not 2, 3 in this set. Therefore, this relation R is an example for the reflexive and symmetric but not transitive in the set A.